June 6, 1944, Normandy, France. A British paratrooper crouched behind a hedgerow as a German Panzer IV rumbled past. In his hands, he held what looked like a black sock stuffed with gray putty. No metal casing. No impressive engineering. Just a cloth bag with a crude mechanism screwed to the top. The German tank commander never saw him move. The paratrooper hurled the shapeless mass against the engine deck. The explosion tore through the rear armor and ignited the fuel tanks. The Panzer IV burned. The weapon that destroyed it cost less than a pack of cigarettes to manufacture. It looked like something a child might make from household scraps. British paratroopers called it the Gammon bomb. German tank crews learned to fear it more than any other infantry weapon the Allies possessed. Before you continue, please take a moment to like this video, subscribe to the channel, and share it with someone who appreciates military history. Your support makes content like this possible. The Gammon bomb emerged from the same desperate circumstances that produced every unconventional British weapon of 1940 and 1941. Dunkirk had stripped the British Army of its anti-tank capability. The sticky bomb addressed part of this problem, but its limitations became apparent almost immediately. The adhesive failed in wet conditions. The glass spheres sometimes bounced off targets without breaking. The nitroglycerin filling was unstable and dangerous. British forces needed something better. They needed something that worked reliably in all conditions. They needed something soldiers could actually trust with their lives. The solution came not from the scientific establishment, but from a frontline officer who understood what infantry actually required. Captain R.S. Gammon served with the Royal Tank Regiment. He had seen combat. He understood armored warfare from both sides. He knew exactly where tanks were vulnerable and exactly what infantry needed to exploit those vulnerabilities. His background gave him insights that laboratory scientists simply could not possess. He had watched men die trying to stop tanks with inadequate weapons. He was determined to give them something that would actually work. Gammon's insight was elegantly simple. The problem with existing anti-tank grenades was not the explosive. It was everything else. The containers were too fragile or too rigid. The fuses were unreliable. The designs tried to accomplish too many things simultaneously. What infantry needed was a weapon that would reliably deliver explosive force to a target. Nothing more, nothing less. Every additional feature was a potential failure point. The first component of Gammon's solution was plastic explosive. Nobel's 808 was a British development based on research into RDX high explosives. Unlike the liquid nitroglycerin used in sticky bombs, Nobel's 808 was remarkably stable. You could drop it, you could shoot it, you could set it on fire. It would not detonate without a proper initiator. The explosive resembled gray-green modeling clay with a faint almond smell from the plasticizer. Soldiers could mold it into any shape. They could cut it with a knife. They could divide it into smaller charges or combine it into larger ones. This flexibility was revolutionary. The second component was even more important. Gammon developed what became known as the always fuse or the delay mechanism. This was the critical innovation that made the weapon work. The always fuse consisted of a weighted striker mechanism inside a metal cap, a length of tape wrapped around the weight, and attached to a safety pin. When the user pulled the pin, the tape unwound during flight. Once the tape fully extended, the weight was free to move. Upon impact, the weight drove forward and struck the detonator. The weapon exploded. The genius of this design was its absolute reliability. The fuse did not care about angled impact. It did not care about surface conditions, wet or dry, hard or soft, metal or concrete. The always fuse triggered every single time the weapon struck a target with sufficient force. The physics were simple and inescapable. Gravity pulled the weight downward. Impact stopped the weapon's motion. The weight continued moving due to inertia. Detonation followed. There was no adhesive to fail, no glass to bounce, no magnetic attraction to overcome. The container was deliberately crude, a stockinette bag similar to the material used for surgical dressings. The bag was approximately 4 inches in diameter and 9 inches deep. It attached to the always fuse cap with screw thread fitting. Soldiers could fill it with varying amounts of plastic explosive depending on the target. Standard loading was approximately 2 pounds of Nobel's 808 for anti-tank use. Against lighter targets, soldiers might use just half a pound. Against bunkers or fortified positions, they could pack in 3 pounds or more. This adaptability was unprecedented in grenade design. The complete weapon weighed between 1 and 3 pounds depending on explosive loading. The empty bag and fuse mechanism weighed approximately 5 ounces. This meant paratroopers could carry the components separately and assemble weapons as needed. A soldier might jump with 3 empty bags and fuse assemblies weighing less than a pound total. Upon landing, he could acquire plastic explosive from supply containers and create 3 anti-tank grenades on the spot. This logistics advantage was enormous for airborne operations where every ounce of equipment mattered. Manufacturing costs were almost negligible compared to other anti-tank weapons. The bag required basic textile production. The fuse mechanism used standard machining processes. There were no precision optical components, no exotic materials, no specialized manufacturing equipment. A factory that made door hinges could produce always fuse mechanisms. A textile mill could produce thousands of bags per day. Britain's industrial capacity was already stretched to breaking point. A weapon that required minimal specialized production was worth its weight in gold. The development timeline was remarkably swift compared to conventional weapons procurement. Captain Gammon submitted his initial design proposals in late 1942. Testing began almost immediately. The Ordnance Board, which had resisted the sticky bomb for months, approved the Gammon bomb with unusual speed. They recognized its advantages. They understood its potential. By early 1943, production had begun. By mid-1943, the weapon was being distributed to airborne and commando units. The official designation became Grenade Hand Anti-Tank No. 82. Training procedures emphasized the weapon's simplicity. Remove the safety cap. Insert the detonator into the plastic explosive filling. Screw the fuse assembly onto the bag. Pull the safety pin. Throw. The always fuse armed automatically during flight as the tape unwound. Standard throwing distance was 20 to 30 yards. Soldiers were instructed to aim for engine decks and rear armor, where German tanks were most vulnerable. Unlike the sticky bomb, there was no requirement to approach within arm's length of the target. The weapon found its natural home with British airborne forces. The 6th Airborne Division trained extensively with Gammon bombs before D-Day. Major John Howard's glider-borne assault on Pegasus Bridge included soldiers carrying the weapons as their primary anti-tank capability. The Ox and Bucks light infantry landed with Gammon bombs because conventional anti-tank guns were too heavy for glider transport. If German armor counterattacked the bridges before relief forces arrived, Gammon bombs would be their only defense. June 6, 1944 proved the weapon's worth. Paratroopers of the 6th Airborne Division scattered across Normandy in the early morning darkness. Many landed far from their designated drop zones. Units became fragmented. Heavy equipment was lost in flooded fields and dense hedgerows. But soldiers who had jumped with Gammon bomb components found themselves with effective anti-tank capability even when separated from their units. They could assemble weapons from supply containers or scavenge plastic explosive from other sources. The fighting around Ranville demonstrated the Gammon bomb's effectiveness. German armored units counterattacked the British airborne bridgehead repeatedly during the first 48 hours. Paratroopers without anti-tank guns engaged tanks at close range using only Gammon bombs and personal weapons. The official history records multiple tank kills achieved by individual soldiers hurling explosive-filled bags at German armor. The weapon worked. It worked reliably. It worked in conditions that would have rendered sticky bombs useless. Private Patrick O'Sullivan of the 9th Parachute Battalion encountered a Panzer for moving through a village street. He waited until the tank passed his position, then sprinted after it. The Gammon bomb struck the engine grill. The explosion set the tank ablaze. O'Sullivan escaped through a garden wall, while the crew burned. His after-action report noted that the weapon performed exactly as advertised. It stuck to nothing. It bounced off nothing. It simply exploded. The hedgerow fighting of June and July 1944 created perfect conditions for Gammon bomb employment. The dense Norman bocage restricted tank movement to narrow lanes between earthen banks. Infantry could approach armor from concealment and engage at ranges of 20 yards or less. German tank commanders quickly learned to fear the shapeless black bags that British paratroopers carried. A single soldier with a Gammon bomb could disable a tank worth 100,000 Reichsmarks. The economics of warfare had shifted. Sergeant Stan Scott of the 13th Parachute Battalion documented his experiences in post-war interviews. "We loved the Gammon bomb," he stated. "It did what it was supposed to do. You could make it as big or as small as you wanted. If you needed to knock out a tank, you packed in 2 pounds of 808. If you just wanted to clear a machine gun nest, half a pound would do it. It was like having a custom bomb for every situation." The weapon proved equally effective against static positions. German bunkers and pillboxes that resisted conventional grenades succumbed to Gammon bombs. The plastic explosive spread across the target's surface upon impact, maximizing blast effect. 2 pounds of Nobel's 808 against a bunker aperture was catastrophic for the occupants. Paratroopers learned to aim for vision slits and weapon embrasures where the explosion would channel into the fortification. Operation Market Garden in September 1944 saw extensive Gammon bomb employment. British 1st Airborne Division at Arnhem found themselves surrounded by German armor without adequate anti-tank weapons. Gammon bombs became their primary means of engaging the panzer units that methodically reduced the perimeter. Lieutenant Colonel John Frost's force at Arnhem Bridge used Gammon bombs to destroy German vehicles attempting to cross. The weapon extracted a price even in defeat. Corporal Tommy Atkins recounted an engagement near the bridge. A German half-track came down the ramp. Thinking we had surrendered, he said. 3 Gammon bombs hit it simultaneously. The vehicle practically disintegrated. After that, they stopped assuming we were finished. The cost of assumptions against soldiers with Gammon bombs was too high. The weapon saw service beyond Western Europe. British forces in Italy employed Gammon bombs against German fortifications during the grinding advance up the peninsula. The Gothic line defenses, which had resisted conventional assault, yielded to close-range Gammon bomb attacks by specialist assault teams. Soldiers would crawl to within throwing distance of German positions, then hurl multiple bombs in rapid succession before the defenders could react. Special operations executives supplied Gammon bomb components to resistance movements across occupied Europe. The weapon was ideal for partisan use. The components were easy to conceal. Assembly required no special tools. Resistance fighters could manufacture plastic explosive from locally available materials if Allied supplies were unavailable. French resistance cells used Gammon bombs to ambush German vehicle convoys. The attacks were devastating and virtually impossible to prevent. The Gammon bomb's versatility extended to engineering applications. Paratroopers used the weapons for improvised demolitions when proper charges were unavailable. A Gammon bomb could cut a telegraph pole. It could destroy a railway switch. It could breach a wall. Soldiers discovered they could use the explosive filling without the fuse mechanism for controlled demolitions triggered by time pencils or command detonation. The weapon was essentially a portable explosive package that happened to also function as a grenade. German responses to the Gammon bomb threat proved inadequate. Sures and armor plates originally designed to defeat Soviet anti-tank rifle rounds provided some protection against the weapon's blast effect, but the plates could not cover engine decks or rear armor. Tank commanders learned to button up completely when infantry was nearby. This reduced their situational awareness and made them more vulnerable to other threats. The psychological impact exceeded the physical damage. Captured German documents reveal growing concern about British explosive-throwing devices. Intelligence reports warned tank crews to maintain maximum speed when passing through areas where British airborne forces were known to operate. Slow movement or stopping invited destruction. The documents specifically mention the effectiveness of British plastic explosives delivered by hand-thrown methods. German armor doctrine had to adapt to infantry weapons that actually worked. Comparative analysis shows the Gammon bomb's advantages over contemporary weapons. The German Haftladung H3 magnetic mine penetrated 140 millimeters of armor, but required manual placement directly on the tank hull. Soldiers had to run alongside tanks and physically attach the weapon. Casualties among troops attempting this were catastrophic. The Gammon bomb could be thrown from 25 yards away. The risk differential was enormous. The German Panzer IV used a shaped charge with canvas fins. Penetration was adequate, but the throwing range was limited and accuracy was poor. The fins did not always deploy correctly. The weapon sometimes failed to orient properly on impact. The Gammon bomb had no orientation requirements. It exploded regardless of how it struck the target. Simplicity was superiority. The American M9A1 rifle grenade achieved good penetration from 50 to 100 meters range. This was superior to hand-thrown weapons in standoff distance. But the M9A1 required a rifle to launch it. Soldiers who lost their weapons or exhausted their ammunition were defenseless. Gammon bombs required only an arm capable of throwing. They worked when everything else had failed. The British putty anti-tank weapon entered service in 1943 and provided genuine standoff capability. Its hollow charge warhead penetrated 100 millimeters of armor at ranges up to 100 meters. But the putty was heavy. It was cumbersome. It was notoriously difficult to cock. The spring mechanism required 200 pounds of force to reset. Some soldiers could not physically operate it. The Gammon bomb was light enough that anyone could use it effectively. Manufacturing statistics reveal the scale of Gammon bomb production. Initial contracts called for 100,000 units by the end of 1943. Production accelerated dramatically after D-Day demonstrated the weapon's effectiveness. By May 1945, over 2 million Gammon bombs had been manufactured. Cost per unit was approximately 2 shillings and 6 pence. This was less than a quarter of the cost of a Mills bomb and a fraction of the cost of the sticky bomb. Distribution prioritized airborne and commando units, but by 1944 regular infantry divisions were receiving allocations. The weapon proved popular wherever it was issued. Soldiers appreciated its reliability. They valued its versatility. They trusted it in ways they never trusted the sticky bomb. Field reports from multiple theaters consistently praised the Gammon bomb as the most effective hand-thrown anti-tank weapon available. Storage and transport presented fewer problems than earlier weapons. The empty bags and fuse mechanisms could be stored indefinitely without degradation. Only the plastic explosive filling required careful handling, and the explosive was far more stable than the nitroglycerin used in sticky bombs. Logistics officers reported no significant incidents involving Gammon bomb components during storage or transport. The contrast with sticky bomb storage problems was stark. Post-war evaluation confirmed the weapon's significance. British Army studies ranked the Gammon bomb as the most effective hand-thrown anti-tank weapon employed during the war. Analysts credited it with destroying more tanks per unit produced than any comparable weapon. The always fuse mechanism was identified as the critical innovation that enabled the success. Captain Gammon received the Military Cross for his contribution to the war effort. The weapon's legacy extended beyond World War II. The always fuse principle influenced subsequent grenade development. Modern impact detonated weapons use similar always action mechanisms that trigger regardless of impact angle. The concept of flexible explosive container filled with varying amounts of explosive depending on target requirements influenced later demolition charge development. British Army explosive ordnance disposal techniques still reference Gammon bomb principles. Captain Gammon survived the war and returned to civilian life. He received minimal public recognition for his invention, despite its documented success. The Royal Commission on Awards to Inventors assessed compensation for weapons developers after the war. Gammon received a modest payment that barely acknowledged his contribution. The man whose invention destroyed hundreds of German tanks received less recognition than many lesser contributors to the war effort. Museums preserve examples of the Gammon bomb today. The Imperial War Museum collection includes complete weapons and component parts. The Airborne Assault Museum at Duxford displays Gammon bombs alongside other paratrooper equipment. Historical interpreters demonstrate the assembly procedure for visitors. The weapon's simplicity remains striking even decades later. It looks homemade because in many ways it was homemade. That appearance deceived German tank crews who learned too late that crude did not mean ineffective. The psychological impact on German armored forces deserves emphasis. Tank crews who faced Gammon bombs developed what modern analysts would recognize as hypervigilance. They scanned constantly for infantry. They avoided stopping near hedgerows or buildings. They maintained speed even in situations that call for careful movement. The psychological burden degraded their combat effectiveness. Fear of a weapon that cost 2 shillings influenced tactical decisions involving vehicles worth tens of thousands of pounds. Veteran accounts consistently emphasized the weapon's reliability. Unlike the sticky bomb, which soldiers remembered for its failures, a Gammon bomb was remembered for working when it mattered. Paratroopers who jumped into Normandy trusted their Gammon bombs to function. That trust was justified. The always-fused mechanism performed exactly as Captain Gammon designed it. The plastic explosive detonated exactly as the chemist promised. The simple bag contained explosive exactly long enough for it to reach the target. The contrast with the sticky bomb illuminates different approaches to emergency weapon development. The sticky bomb emerged from laboratory experiments by scientists and engineers who had never experienced combat. The Gammon bomb emerged from the practical experience of a frontline officer who understood exactly what infantry needed. Both weapons addressed the same problem. Only one solution worked reliably. June 1944 British paratroopers descended on Normandy carrying black cloth bags filled with gray putty. The bags looked absurd. They looked like toys. German tank commanders learned otherwise. The Gammon bomb destroyed more German armor than any hand-thrown weapon the Allies possessed. It worked because its designer understood that simplicity was strength. It worked because its designer prioritized reliability over sophistication. It worked because Captain Gammon understood that infantry soldiers needed weapons they could trust with their lives. The ugly cloth bag became the most feared weapon in the British infantry arsenal. German tank crews dreaded it because it worked every time. It never failed to stick because it never tried to stick. It never failed to break because it had nothing to break. It never failed to detonate because its fuse mechanism was as simple as physics allowed. British engineering at its finest looked like a stuffed sock. That sock killed tanks. That was all that mattered.